Shall we start? Let's start. Our second speaker of the morning is Rachel Webb from Michigan, is that correct? Who's going to tell us about the virtual cycle on the modular space of maps with complete intersection.
Thank you. So my talk is part of the story of computing the Gromov-Witten invariants in the quintic. So I'm going to start by recalling that story. I think most of us have heard it before, but I want to tell it again so I can explain exactly how this theorem that I'm going to present fits into that story. So Gromov-Witten invariants are defined within a moduli space of stable maps. And the moduli space parameterizes maps from nodal curves to the target with specified genus and markings and degree. And they should be stable so that they have finite automorphism groups. And the information I'll use today is a forgetful map to the moduli of pre-stable curves. And just to remind you where Gromov-Witten invariants come from, there are evaluation maps to X at the marked points. And so this moduli space has a perfect obstruction theory. Which, via the construction of Baron and Quintic, leads to a virtual fundamental class. And it's that class that lets you define the Gromov-Witten invariants. The invariants are integrals against that virtual class. Of pullbacks of cohomology classes on X. So from my perspective, the objects I'm studying here are the virtual space, the moduli space and its virtual cycle. So we have this theory of Gromov-Witten invariants, and both mathematicians and physicists are interested in actually computing these numbers. And an example that has gotten a lot of attention is the quintic. Hypersurface. In P4. So in genus-zero, this was first done by Giventhal and Yan Yao. In the mid-90s. And the strategy was to use quantum Lefschetz to relate invariants of the quintic to invariants of the ambient space P4. The nice thing about P4 is that it has a torus action that lets you do torus localization. And quantum Lefschetz is something special to the genus-zero that doesn't immediately generalize to higher genus. So higher genus computations need something significantly different. So genus 1 was done by Zinger And we would kill Zagier about 10 years later. But these methods do not generalize to higher genus. And so yeah, so to go beyond that, again, you need something new. There's lots of different approaches to doing this. The approach I'm going to talk about today uses an auxiliary moduli space called the moduli of p fields. So I'm going to write the p field theorem on the sideboard here. So,
slight objection. This is not going to be on camera, and people who
oh,
are
I
there
didn't
cannot
realize
see
there was a
it.
camera. Okay, well, then I will just write it over there. And I didn't realize there was a thing there. Thank you. Then I'll just have to erase it later, and we will look at that. Well, we'll see. Maybe I'll not erase it. We'll see how much space I need. So this theorem, a lot of people have, what I'm going to write down here that is due to a lot of different people. So half of it maybe is the cosection localization of Qile and Li. Chang-Li, as far as I know, I'm not very good at history, so maybe other people even had these ideas before Chang-Li, but so far as I know, sort of the original statement of this theorem comes from a paper by Chang and Li, but only at the level of Gromov-Witten invariants. And the theorem I'm going to write down is going to be about moduli spaces and virtual classes on them. And so that version of the theorem was also done by Kim O and Chang with a different Li. So the theorem. There's a moduli space of p fields which parameterizes now stable maps to P4 together with I can pull back the bundle O of 5 that cuts out the quintic. And my extra piece of data is a section of the dual of that pullback tensor with omega. So F should be a stable map. And then I have some section. And so this is the moduli space, and the theorem is that this has a cosection localized virtual class. So I'm going to talk more about what that is. The cosection is going to be determined by the quintic, by that function. And the cosection localized virtual class, what that is saying, but what I'm writing down is a description. The theorem statement tells you what this does. So it's a class that lives in the Chow group of something smaller. So this should be a virtual class on this moduli of p fields, but it's actually supported on a smaller locus. It's actually supported on the locus of maps to the quintic. But it's pushed forward is some virtual class, not cosection localized, on this space. On the moduli of p fields. And really, so really the key points of the theorem is the equality that I'm about to write. which is that this cosection localized class is in some sense dual, or it's very, very closely related to the original virtual fundamental class on the moduli it maps to the quintic. The difference is just a sign. Let me draw some pictures to try to explain what's going on. So I have this moduli space of p fields, and this is a cone over the original moduli space of maps to P4. So I have my moduli maps to P4, and above that I have my M, which is a cone, so it could have some fibers of larger dimension. And then living in the moduli maps to P4, I have a substack, which is my moduli of maps to the quintic. And so this locus of maps to the quintic is itself contained in my big P field moduli space. So that's where this is all coming from. The theorem is that you can construct a virtual class on the big moduli space of the moduli of P fields, but it's actually, that class is actually supported on maps to the quintic. And in fact, it is it's like the same thing as the virtual cycle on the moduli maps to the quintic. And so the idea of using this theorem to compute invariants is, now I've realized my virtual class for the quintic as a class on a bigger moduli space, which does have a torus action. So like this original strategy used torus localization. If you still want to use torus localization, first you need something your torus acts on. There's a torus action on this P fields moduli space. There's like the cone direction, and it's over maps to P4. And so I've got lots of torus there to work with. So the point of this P fields theorem is that, for example, in genus 2, my co-authors, along with some other people, have a theory of a logarithmic gauged linear sigma model, which, so you've defined this P fields moduli space. To do torus localization, you still want to compactify it. It's not compact as it is, but you do that, and that gives you a strategy to compute these higher genus invariants, still using torus localization. To do these computations. And the general theory here, it's general, it's not special to the quintic, it works for other targets as well. And so the problem I'm presenting today is a generalization of that P fields theorem to arbitrary targets. So this works for fairly general targets. And what I want to do is generalize this. So I'm going to delete this little sketch and add something about our setup for notation. So this original P fields problem has a bundle of 5 over P4 with a section, the quintic polynomial, which cuts out a hypersurface, the quintic. So my notation, I'm going to look at a target Y. Y can be a smooth projective variety. Our theorem holds for any algebraic stack with a smooth Deligne-Mumford substack. So if you take Y to be a GIT quotient, our theory recovers a P fields theorem for quasimaps. But you can just think about Y being a smooth projective variety for purposes of exposition. And we have a vector bundle on Y with a section that cuts out some zero locus, like so. And right, and so the other thing I sort of wanted to diagram here is that with the quintic setup, we had, lacking in space, we had moduli, so this thing I defined, this moduli P fields was a cone over maps to P4. I'm going to omit the genus and number of markings. They don't play any significant role in the story I'm telling today. And contained in that, we have the moduli maps to the quintic. So our theorem is very general in that, so I have this very general target, some algebraic stack with a smooth Dilly-Mumford substack. What is my moduli of stable maps? Well, if this is a smooth projective variety, then our theorem, you just plug a moduli of stable maps here with some genus markings of degree. If this is more general, what I'm saying is our theorem works where you choose. You get to choose this stack, and it just needs to be a smooth, or not smooth. It needs to be a Dilly-Mumford separated finite type stack of maps to Y, and you get to choose what that is, and our P fields result applies to that. But natural choices would be your usual moduli of stable maps. So we will construct a moduli of P fields over this, and our MX, this should just be maps to X that are stable as maps to Y. I'll come back to this notation again later in the talk, but I wanted to at least get it on the board to sort of show us where we're going. So the goal is to replace this notation with that notation and essentially keep the same theorem. Questions? Okay, so so I do want to emphasize what I'm choosing here. What are the inputs? You are choosing this information and you are choosing this information subject to certain constraints. Those are the inputs to the P-fields problem, as we stated. So now let me explain our result, how that works. I'm going to start by telling you about the moduli spaces. So what is the moduli space of P-fields? I'm going to take the time to digress a little bit maybe. And, well, we define our moduli of P-fields. I mean, it's like the same thing as this, but we state it in a different way using the moduli of sections. And the benefit there is that it looks, our statement, it looks more like a gauge linear sigma model, and it makes things run better. So I'm rather fond of this perspective. So if you have an algebraic stack over a family of curves, so this here is a family of curves. I'll do some specific examples in a minute. But then define the moduli of sections of Z over C to be mirroring how I've been describing these moduli spaces. It should parameterize fibers of this family of curves. So I should pick some fiber of my family together with a section of Z. So this should all be like a commutative diagram, and this bottom part should be fibered. And so a theorem due to Hall and Bride is that this is an algebraic stack with basic good properties. You need basic good properties on Z. And then you get that this moduli space is algebraic with basic good properties, quasi-separated, locally finite type, things like this. The nice thing about this general setup, so there's universal data. I should say an algebraic stack over whatever base I was using. And so it has a universal family, like so. With some universal section, I'll call it N. And there's a canonical construction here, a canonical way to get an obstruction theory. And essentially that obstruction theory is like the derivative of this universal section. It's the canonical map of cotangent complexes, relating these two cotangent complexes. So I take the cotangent complex of Z over C, and I pull that back. And that has a map to this cotangent complex. Tensor with omega, and push down, and then there's a trace map to this cotangent complex. So there's this very canonical construction, and it's an obstruction theory. So this is the thing you should be familiar with when I restrict, say, to like the locus of stable maps in here. This restricts to the usual obstruction theory. Various things in this picture could be algebraic stacks. So this is a three-term obstruction theory. It's an isomorphism in degrees 0 and 1. It's surjective in degree -1. But this is, in complete generality, this is an obstruction theory. And so the point is now we can take various specializations of this construction. So the first example, which maybe you've already discerned, is that this is a very slight generalization of the construction of maps to some target. So we choose Y, like over there. So in general, our theorem holds, again, for an algebraic stack with a smooth Dilley-Mumford, non-empty smooth Dilley-Mumford locus. Or we can just, for simplicity, say a smooth projective variety. And so then what you want to do is you want to set your U to be the moduli of free-stable curves with some genus and markings, and C to be the universal curve there. And then your Z should just be C cross Y. And now this moduli of sections I'll just call it the moduli of free stable maps to Y. And our usual familiar moduli of stable maps is a certain substack of this one. So if you're working for Y is a smooth projective variety, then we have like an obvious choice of substack of this guy, which is stable maps. In general, our theorem is choose a substack. That is Dilley-Mumford, separated, and finite type. So this also works for quasimaps. And we also want to choose it so that this phi restricts to a perfect obstruction theory. which will give us the construction of a virtual fundamental class on MY. So once we've done this, we can construct the moduli of P fields by keeping the same U and C, and now I want to choose Z. So if I have a vector bundle E over Y, I want to choose Z to be the total space of a vector bundle on this guy. And the vector bundle should be omega pulled back from the C factor tensor with E dual on the Y factor. And so this, let's see, maybe I can modify this picture right here. So now I have C cross Y, and this is M. And I have, sure, for this universal family, I can say I have this one. Anyway, and so now I have another thing on top of that, which is, I'll just say omega tensor E dual. And so now I can look at moduli of sections for this guy. So I have, using this thing right here, by composing with this structure map, I have a map to the moduli of sections. Oh. I have a map to the moduli of maps to Y. And I've already chosen my good Deligne-Mumford substack of this one. And so I just define the moduli of P fields to be the fiber product here. My notation for the moduli of P fields will be like so, with adding the notation of the vector bundle E. This is how we define the moduli of P field. So just to compare it with what I have over there, now I'm taking a section of the section and the stable map are part of the same data. It's completely equivalent, right? Taking a section like so is the same if I pull back this thing over here and take a section of that. These are completely equivalent, but we are viewing the stable map and the section as a part of the same data. Yeah.
Sorry, so I know that one's supposed to just think it as a black box, but how should I think now concretely of the abstraction, of this like L sub stuff? And so, I mean, where do they live? What do they mean?
This?
Yes, now I'm getting confused about these guys.
What is your question exactly about them?
Well, so where do these things live again?
So this is in.
What are they concretely on these examples?
In these examples, yeah. Okay, sure. So, for example, this object is in the derived category of the moduli of sections here. And this L started out in the derived category up here. I pulled it back with N and I pushed it down.
Okay.
So now everything is in the derived category right here. And so like if this is the moduli of stable maps to P4, now this is the cotangent complex for moduli of maps to P4. And this piece, because it comes from the cotangent complex of like the quintic, which is smooth.
Where did the quintic come in?
I didn't mean to say quintic. I meant to
Sorry,
say P4.
it's still P4. Okay, thanks.
Yeah, P4, which is smooth. Its cotangent complex is just a vector bundle in degree 0. And so this whole thing, then I push forward. So here I'm getting something that is perfect in 2 degrees. So I have this nice like vector bundle approximation of the cotangent complex.
Okay, thanks.
Yeah, thank you. So I have this moduli of P fields, and the point is that this map here is really nice, because my Z was just a vector bundle on this one, So this map here is going to be affine, like represented by affine schemes of finite type. So this map is really nice, this map is really nice, and so we get good properties of our moduli P fields just for free. Like there's nothing, I have not presented any deep maths to you yet. I'm just explaining the setup. So we get good properties of this moduli P fields just from these assumptions. So this will be the Mumford separated finite type. And the canonical obstruction theory will be perfect as well. So I have a canonical virtual fundamental class on this moduli P fields. And that canonical virtual fundamental class is this one right here. So what I have to do now is construct the cosection localized one. Or what I need to do is explain how this thing is supported on some substack of maps to X, and how that localized virtual class is the same as the canonical virtual class for maps to X. Okay? So that brings us to virtual fundamental classes. So I just want to review like the inputs and outputs of Baron and Penteke's theorem. So their theorem says the input is exactly this phi, or any phi. That's a perfect obstruction theory. And I'm using the notation that I guess sort of comes from this example. So I have some nice thing over my base. So if I have this relative perfect obstruction theory, then I can define from that a virtual fundamental class. So this should be a morphism in the derived category of M. And the cosection localized version of this construction says we should have this, we need this phi, and then we also need one more piece of data, which is a cosection, which I'll call sigma, from the dual of E to O placed in degree 1, such that, so, I mean, the story of how this, big picture of how this construction works is you take the dual of this, you truncate to the first 2 degrees, and then you apply a canonical way to turn a 2-term complex into a Picard stack. And once you do that, you've turned this around, this thing becomes the intrinsic normal sheaf, which contains the intrinsic normal cone, and this turns into some cone stack defined off of E. So we've got the intrinsic normal cone sitting inside of a cone defined by E. And then this class is the intersection of that intrinsic normal cone with the zero locus. Cosection localized says I want that intrinsic normal cone to land in the kernel of the cosection. Okay? So the such that here is precisely that requirement. Such that, so I had to turn this around, right? and then I want the intrinsic normal cone to land in the kernel of sigma. So I'm trying to keep this at an understandable level, so maybe I'm losing a little bit of precision, but this is precise if you're thinking of statements on cones. That's what I mean by the composition is zero. And you could make sense of it in the derived category as well. So once you have this information, then I could intersect that intrinsic normal cone coming from this one. I could intersect that intrinsic normal cone with the zero locus in the kernel cone stack of sigma. And that is your cosection localized virtual fundamental class. And so like by definition, I was working over the kernel of sigma. So this thing will be contained in the child group of what is sometimes noted M of sigma. So this is the locus where sigma is 0 on M. Again, thinking of like a map of cones. So I have a literal like cone stack that is the kernel, and I look at where that thing is supported, and that's M of sigma. So their theorem is that the inclusion of this cosection localized class is the same as the usual fundamental classes you would have gotten if you ignored this cosection and just did the usual variant quintic construction. And the benefit of this construction is that M might not be compact, but your zero locus might be compact. And that's what happens in the P field situation. M is not compact, but the degeneracy locus will be compact, and so that lets you define invariants of your moduli space or of your target. Okay. Am I missing anything? Has this explained any questions? I'm trying to think if I said everything I wanted to.
So concretely, P fields are going to go to stable maps to the subscheme X inside Y, right?
P fields are going to go to
once I look at the cosection localized moduli space over Y, it somehow is supposed to single out the moduli space of maps to X inside Y.
Yeah, so I'm going to do example now of this thing, like right here. And tie this up with our situation. So what is the cosection? Or the moduli of P fields. So we've chosen our section S over there. This is a section of E. So I should assume, maybe I'll write these ones down because they're important. I haven't written down most of our assumptions, but we're assuming that S is a regular section. And that the zero locus is smooth. Even without those assumptions, given a section, you get a function on the dual of E. And this rule is just, let's see, so if I have an element of this dual, I have some function on a fiber of E, and it's based at a point, say, little y and y. And so what number does that map to? Well, I have that function, and what can I feed it? I can feed it s of y. So this will be a linear function, a function linear on the fibers of E dual. And I think I just erased my universal family. So if I draw my universal family again for the moduli of P fields, I can take this and tensor it with omega. So this is essentially W right here. And remember that my perfect obstruction theory came from this relative cotangent complex, like the derivative of this map, essentially. So my cosection is going to be basically the derivative now of this map. So there's a map of cotangent complexes from this one to this one. And I can, when I pull that back tensor with omega, push it forward, this relative cotangent complex turns into O. So this, I'm being sketchy here, but, and then I have to take a dual at the end. But we get a cosection of the canonical perfect obstruction theory. Oh, let's pull back. So again, that O comes because, like from duality, from this relative cotangent complex. When I pull it back tensor with omega and push down, it turns into an O. So that's roughly where the cosection comes from. It comes from this section of the original setup. And so what we want is we want the degeneracy locus, the zero locus of this cosection, to be precisely maps to X sitting inside of Y. And, I think I could not find the right place in my talk to write this down, but I want to be a little bit clearer about what my MX is over there. What I mean by MX, so this should be the analog of maps to the quintic, but in the general setup, what I mean, I've already chosen this locus of good maps to Y, and that is sitting inside of like all possible pre-stable maps to Y, and I just want to intersect that with all possible pre-stable maps to X, and that's, so like in the quintic case, that's like why there's an I lower star beta in that theorem over there. These are, you should think of this as maps to X that are like stable good maps as after you compose with maps to Y. So, point is we have this MX sitting inside of this one, and we want the degeneracy locus of this cosection to be precisely MX, and that's where we need those assumptions on S. And that is not exactly trivial to work out, and that's part of our theorem, is that the degeneracy locus of this cosection is MX. So I'm going to write down our theorem now. So there's moduli space of P fields, which is this thing I've defined. With a cosection localized virtual class, and part of our theorem is that the degeneracy locus is actually this moduli maps to X. Such that, so this is just the cosection localization theorem of Chang-Li. We don't need to do any work here. So that the push forward is the usual fundamental class, and the I should have written that. This is an inequality in the Cha group of maps to X. And so in that smaller Cha group, we have that these classes agree up to a sign. And the sign that I take now this is, how do we use? It's some Euler characteristic. So this is a function that is constant on connected components of mx, and at a particular closed point of mx, so that corresponds to a stable map to x, you pull back E, and you look, and this is equal to the Euler characteristic of that pullback. So I can write that down. Where the value of this function at a closed point corresponding to a certain curve and stable map is the Euler characteristic of upper star. Okay, and then the remark is that, so I just generalized a whole bunch from the particular quintic theorem I had written down earlier. Some other people before us did partial generalizations, like in between here and there. So when Y is projective space and My is quasimaps, this theorem is due to Chang-Li. If Y is a general GIT quotient of a vector space, and again for quasimap theory, this is due to Kim and O. So this theorem, Kim and O's result, is pretty general already. The most important thing that ours adds is the situation when X is not a GIT quotient in the context that is allowed for quasimap theory. So quasimap theory requires an affine variety with only LCI singularities. And so there are certain situations, there are even potential applications of this theorem to targets that can be written as a GIT quotient in that way. Any questions? Yeah?
So to use your theorem to compute, let's say, some higher-genus invariants, in the case where you have a lot of torus actions on the bigger space on Y, so implicitly you're saying somehow that this virtual class on Y is torus equivariant in that setting, even if there's torus action doesn't preserve X or doesn't preserve your section, right?
Like that the p-fields class will be torus
Yeah,
equivariant?
that's right.
I think that should be true. If you have a torus action, I guess I don't know. I guess I don't know about the cosection localized statement. Is there more to your question, or was that the concept of it?
So I'm trying to imagine, like, if you want to compute the invariants for X, you now express them in terms of Y, and now you want to use, how can you now express them in terms of different, let's say, different calculations specific to Y?
I think the short answer to your question is I don't know. So my co-authors are really the ones who do this computation. I haven't done anything of that. So, and there's a big other piece of theory, which is the log gauge linear sigma model, the compactification of the p-field moduli space. That's a big thing that I don't know anything about. So yeah, it's not a part of the story, I understand.
Okay.
Okay, so I have just a few minutes left to draw some pictures about why you should believe this theorem. The first reason you should believe this theorem is that you've seen it before in a non-virtual setting. So if we look at the target information, I'm going to draw some pictures. So here we've got Y, and we have a vector bundle E on it, and it had some section that cut out a zero locus. So the theorem that you've seen before, I think that this theorem, it probably exists in a lot of contexts. The one I'm familiar with comes from Fulton's intersection theory. But there is a localized Euler class which I'll write E sub s for the section S. And the point is that this lives in the child group of the zero locus, but it pushes forward. And in fact, it doesn't just live here. The localized Euler class is equal to the fundamental class of X, and it pushes forward to the usual Euler class. So this, what I'm writing down here is the statement that the Euler class of a vector bundle is the class of the zero locus of a generic section. That's what I'm writing down. So that's probably a familiar statement if you've ever done anything with Euler classes. I would expect you would be familiar with that. And that's really what I'm saying virtually over there. The virtual fundamental class is an analog of the Euler class. And the cosection localization is an analog of this localized Euler class. And in fact, this is actually a special case of that theorem. So you can write down a perfect obstruction theory just on this, like forget about moduli maps. You can write down a perfect obstruction theory on this, so that theorem exactly, like the definition of this localized Euler class is the definition of the cosection localized virtual fundamental class. So this is a generalization of something you've probably seen before, and that is one reason you should believe it. I can also tell you a little bit about our proof, draw some pictures of our proof. So there's two main steps. The first is deformation to the normal cone. And that step is constant across like all of these various people I've said have done various p-field theorems. They've all done some kind of deformation to the normal cone. The second step is unique to our approach. So I'll tell you in a minute what that deformation looks like. We get some special fiber. The general fiber is like the general setup we started with, and then the special fiber will be something where we can do torus localization. And that's unique to the p-fields problem. So the deformation to the normal cone. I'll remind you what that geometry looks like. You have a base A1. And you take you cross it with Y. And we have our zero locus X sitting inside of Y. And I take X cross 0, and I blow up along X cross 0. So what that does is it adds the projectivization of the normal directions to X cross 0 in that product space, which is the same as just adding the projective closure of the normal bundle to X and Y. And then I remove the original copy of Y. So now the fiber over 0 just looks like X sitting inside its normal bundle. And that is the construction of the deformation to the normal cone. So now I have this total space of a deformation, and it has two projections. It has a projection to A1 and a projection to Y. And the idea here is to deform the p-fields problem. So to do that, I also need to deform the vector bundle and the section. So I have a vector bundle on Y. I could just pull that vector bundle back to the deformation space of the deformation. That's not quite the right thing to do, because when I pull back the section, my section over here vanishes on X. So when I pull it back, it's going to vanish on this entire fiber over 0. We don't want that. We want it to vanish just on X across the 0, across the whole thing. And so the way to fix it is just to twist down by that fiber over 0. And now it has a section, like the reduced section. And so now I've described a p-fields problem. I have a vector bundle in a section, and the 0 locus of the section is now like the 0 locus I care about. So the point is that st tilde vanishes on X cross 1. And so step 1 is to show for us is to define the moduli space of p-fields for this setup. It's just a little tricky with stability, like sort of from what I described before, that there's something to figure out about the stability, what the stability condition should be. But we define a moduli space of p-fields to this whole setup and show that the fibers are the p-field moduli problem of the fibers of this deformation. So on the one hand, the general fiber, we recover the p-fields problem that I began with, and in the special fiber, we get the p-fields problem for this geometry. So let's investigate what that geometry is a little better. Right there in the fiber over 0, we have X sitting inside of its normal bundle. Because my section was regular, the normal bundle to X and Y is identified with E. And so this is X as the 0 locus and E restricted to X. But on the other hand, what is the vector bundle that I have is E again, pulled back over itself. So now this vector bundle is E on itself. So this is something very special. And this section, what does that restrict to? It restricts to the tautological section. So sending a point in E to that same point in the fiber above it. And the observation is that there's a good C star action here by scaling fibers of E, and the bundle is linearized by taking the same action, right? So I just have some nice C star action, and that makes the tautological section equivariant. And this is a context where you can do a cosection localized torus localization. So it's a fancy version of torus localization. And this version of torus localization is due to Chang, Qile, and Li. So we can do that, and what is the fastest way to show you what happens? Right. So what is the? So I guess the theorem. So I have a moduli of p-fields where my ambient space is now this Ex, and the vector bundle is E again. The torus localized cosection localization theorem says that this is the same as I have an associated virtual fundamental class on the fixed locus, and I should divide by the equivariant Euler class of the normal bundle. So this I here is pushed forward from the fixed locus. So the first key observation is that the fixed locus of this torus action on the target is just X. So on the moduli of maps, the induced action fixed locus will just be maps to X. and that is the same as our degeneracy locus for the cosection. So a lot of this simplifies. Like there's no cosection localization there. There's just some virtual, this is now just some virtual class defined by the fixed part, whatever it is, of the obstruction theory. And this is something defined by the moving part of the obstruction theory. So now all I need to do is decompose this obstruction theory into its fixed and moving pieces. And I mean, what's going on there is it comes from this canonical distinguished triangle or short exact sequence, really, in this case. So this is my Z, which happens to be a vector bundle over C cross X. And so the original obstruction theory that I'm interested in, my original P-fields obstruction theory, is going to come from, let's see, this one over this one, and that's going to decompose into a complex with this one over this one, which will be fixed because X is fixed. And this cotangent complex is exactly what's used to define the perfect obstruction theory of this guy. So my claim is that this tower of maps leads to a DT, a distinguished triangle of this cotangent complex mapping to this cotangent complex, which is the one that is implicit here and here, is this one in the middle. Mapping to this one. And I claim this is the fixed part and this is the moving part. And this fixed part is exactly the same as by definition, it's the same as the virtual fundamental class canonical one on X. And this moving part has an E and something like the dual of E. And when I push it forward, so this top part, yeah, this is just, I'll just leave it as it is. This is the canonical virtual fundamental class. And this moving part, so this is the fixed moving, the moving part, because it's basically like E and E dual, once I push it forward, I get a sign that is equal to the Euler characteristic of E. So that's where the result comes from. Any questions?
So this last question, can you evaluate this in terms of the torus action by fixed points of the torus action? I mean,
This expression?
yeah.
Evaluate.
I mean,
Evaluate. So this is the P fields. So by part one, this is the P fields virtual class. By step one. And this is the usual construction of the virtual class.
yeah, but I mean, if you are in the quintic and you have this torus action in the special fibers, can you evaluate this expression explicitly, getting numbers? Or?
So like using this torus action, you're asking if I can evaluate something on this side? Yeah, no, so this torus action was just to let me relate the P fields class to the usual class when I have this very special geometry. So this is just sort of like an auxiliary torus action, not related to the ones you hope to use
In order
to compute higher-genus invariants. Yeah. Yeah.
So Kim, as far as I know, Qile, they did this cosection, and this cosection is from this absolute.
Oh yeah, good question. So they work with a much more general setting. So they consider, what do they call it, meromorphic cosections that don't have to be defined everywhere. So you can check we do check in like an appendix of our paper that what I've written down here recovers the absolute. All you need is this condition, and then you will get an absolute cosection. And they have some condition like the cosection descends or something like this. Like they have some technical condition. This is sufficient. We have a nicer situation than what they deal with in their paper. And for us, all we need to check is this, and then you recover the conditions in their paper that they need.
Any other questions? That's Rachel.
Yes, I think so. You should check. Yes, it is swapped because David Fabero has to leave today. He got a complaint.
Oh, I see.
Would you example that we talked about
Right.
Yes, and so, yes, so you should know the two talks are swapped. Fabero first.
Oh, okay.